8.2 equations of planes. So we're going to move on our study from vector and parametric equations of lines and looking at vector equations of planes. So there are a couple of ways we can define a plane in 3D space. So we can define a plane using a point, okay, point A, okay, and along with that point, we would need two non-collinear vectors, okay, so like vectors u and vector v, or a vector a and vector b, okay, and so that would look like this situation right here. You have a plane, the point, and two vectors that are not collinear. That can define a plane. And when I say define a plane, we're saying can I determine any vector point on this plane, and I can do so if I have one point on the plane already and two other non-collinear vectors. Okay. You can also define a plane with three non-collinear points. Okay. Simply because I can create two vectors from those points that are non-collinear, and then you have a point, one of those 3 points, and then just like the first situation, yeah, you have two vectors and a point, and you can define a plane. Okay. So here's how we define a plane. We're going to use R to be a position vector for any point on the plane. Kind of like, here's the point you're trying to solve, right? Like it's like the equation of a line. You're trying to find y equals mx plus b. What is y, right? For a position vector, we have x, y, z. What is that position vector for any point on the plane? Okay. And so as we said, we can define a plane as long as we have a knowledge of an existing point, a known point on the plane. So we'll call that R0. And of course, two non-collinear vectors, uv or ab, and these vectors are non-parallel direction vectors, and they're on the plane. Okay, and we're going to need to use scalar values for these parameters. T and s are going to come back again. Okay, and so the equation of a plane is simply, well, vector r equals the known vector point r0 plus some scalar multiple of vector a and some scalar multiple of vector b. Okay, or we can express it in this kind of this vector form here, where you break it into components. So vector r is a component x, y, z. R0 is a component x0, y0, z0, and your vectors a and b are here, a1, a2, a3, and b1, b2, and b3. Okay. So again, what this formula tells us is that I can find any point P on this plane as a scalar multiple of vector A and vector B from a point that we already know that's on the plane, right? So I could say I could find point P if I add vector B however many times, right? And then add A however many times to that. So all I need is a starting point, add those scalar multiples of vector B and add the scalar multiple of vector A, and I'll arrive at that point that I want on the plane. Okay, and any point on the plane can be defined this way. Okay. Parametric. So let's fill in our notes here a little bit. So this is, again, just to make sure this is a point, or like a point vector, and then these two vectors here are your direction vectors. Direction vector A, and you have direction vector B. Okay. And just like vector equations of a line, we can also find the parametric equations of a plane. Okay, and so you just expand the above vector equations just to get the parametric forms, right? So you have x0 times t times a1, s times b1. Okay, if we just change this up a little bit, what if we were using u and v as our direction vectors instead of a and b? Well, you would just have the same letters. So instead of a and b, I have u and v, right? So it's always going to be the initial position vector plus the scalar multiple of your direction vector component plus the scalar multiple of your other direction vector component. And s and t are different scalars, of course. And so that's just the parametric equation of a plane. If I was using a and b, here's how it would look like, right? So I would just say x equals, so I'm just taking this x up here, equals x0, your x component of the point vector, plus t times a1, okay, plus SB, so plus S times B1. Okay, and that's your parametric equation in X. If I'm looking at the parametric equation in Y, so again, look at the Y there, Y equals Y0, the initial point vector, plus A2 times T, so T A2 plus S times B2, so plus S times B2. And then the Z component, let's just clear some of this here. Okay, so for the Z component, again, we're looking at Z equals Z0 plus A3 times scalar T plus B3 times the scalar parameter S. Okay, so Z0 plus T times A3 plus S times B3. Okay, and so again, the textbook might use U and V. It might use a different set of letters, um, but it's all the same process. Start with a point vector, the initial point on the plane, and then you add scalar multiples of the two direction vectors. Okay, so we'll go through a couple of examples of how to find this equation. So just before we do, then a couple of notes here. So notes that the constants on the right side of the equations are the coordinates of a point on the plane. The coefficients of S and T are the components of the direction vectors on the plane. And the parametric equations are not unique since we can use any point on the plane and two non-collinear vectors on that plane, right? So like, just like to think of it, like, the equation of a line is just, one representation, there's three representations or whatever, how many representations. You can create a set of equations for a plane, but those are not unique, right? They're, you can write many, many different kinds of equations that represent the same plane because you just need two vectors on the plane and a point. But here's an example how we work out how to find those equations. So find the vector and parametric equations of a plane that contains point A, point B, and point C. So this is a scenario where we have 3 points. Okay, all we need is 3 points to define a plane. So from those points, you create two direction vectors. So create two direction vectors, and so I'll create one by joining point A to point B, and if I join point A to point B, that vector will be so 1 minus -2 for the x component, 5 minus 3 for the y component, -3 minus 4 for the z component, and that would be 3, 2, and -7 for that vector. And I can create another direction vector by connecting point A and point C together, and that would be -3 minus -2 for the x component, -1 minus 3 for the y component, and 5 minus 4 for the z component, which would give me a vector of -1, -4, and +1. Okay, so I created two vectors, and you just want to make sure, check that they are not collinear. Okay, so you kind of want to check that your vector that you create, vector AB, is not equal to some scalar multiple of vector AC. Okay, so when you check that 3, I go, okay, well, 3 divided by -1 is -3, 2 divided by -4 is -0.5, -7 divided by 1 is -7. So yeah, all 3 components would have a different value of k. It's not collinear, so not to worry there. We're good. Okay, if you end up having all the same, if they're all proportional to each other, then that means you have a collinear vectors here. So we don't have collinear vectors, so we're good. Okay, so the vector equation of my plane would simply be, okay, x, y, z, right? So some x, y, z is equal to the starting point vector. You have 3 points to choose from, okay? None of them are wrong. They're all on the plane, right? So you pick one of them. I'll pick point A for simplicity. It's just the first one, so -2, 3, and 4. And then plus, and really I'm picking point A because I created my vectors A and B and A and C, right? So that makes sense, right? If I have point A and point B, it just makes sense. If I make a vector here and here, and and let's say point C somewhere, and I make a vector here, right? So just starting from point A, and you're just adding scalar multiples of A, B, and then AC, right? So that makes sense, right? So if I start from point A, however many multiples of A, B, and then multiples of AC when I add them, and there you arrive at a point somewhere on the plane, right? Okay, so that's kind of the idea. So starting with point A plus scalar multiple of AB, which is 3 s times 3, 2, and negative 7, plus t, scalar multiple of t of vector a to c, which is negative 1, negative 4, and positive 1. Okay, and then so that's my vector form. For my parametric form, I just take out the components. So x would be negative 2 plus 3s minus t. Y would be positive 3 plus 2s minus 4t. And then z would be positive 4 minus 7s plus 1t. Just separating the components. Okay, so that's how we do get the equation. Example number 2, determine an equation for a plane that satisfies the following set of conditions. The conditions are that it is parallel to both the y and z axis and contains the point A. So x, y, and z is equal to, create those vector brackets there, equal to your starting point, negative 4, 5, and 1, plus some scalar multiple of one direction vector plus another scalar multiple of the other direction vector. And I'll use s and t for those scalar multiples. And the question is, what is your direction vector? And the clue is that the direction vector, the plane is parallel to both the y and z axes. Okay, so they're parallel to some set of, y. Okay, so here if it's, let's say x, y, and z, if it is parallel to the y and z axis, this plane has to be parallel to the y and z axis. And then it makes sense that you have a direction vector along y, and you have a, let's do that different color. You have a direction vector along the y axis, and you have a direction vector along the z axis. And so what vectors do we know that are along the y and z axis? Well, we know what the unit vectors are, right? The unit vector I is a vector along the y-axis. We define that as 0 and sorry, not y, it's j. I is x, right? So j, the unit vector j is the unit vector along the y-axis, so 0, 1, and 0. And unit vector k is along the z-axis, which is defined to be 0 and 0 and 1. So I can use those vectors to be my direction vectors for this plane, right? So even though the plane may not be aligned perfectly with the y and z axis, we know for sure that it is parallel to the y and z axis, right? So if I just took the plane, shifted it over, right, like it's the direction vectors along this plane are still the same direction vectors I could use for the unit, like they're still the same vectors like the unit vectors, 0, 1, 0, 0, 0, 1. They only specify the direction, so they are parallel, so I can still use those vectors no matter where this plane is, as long as the plane is parallel to the y and z axis. Okay, and so we have 0, 1, 0 for one of the direction vectors and 0, 0, 1 for the other one. It doesn't matter the order really, as long as you include them both. Okay, so I ask you to read the other examples in the textbook for this section, and you can work on some of the practice problems for this concept. All right, ending the video.